Hi everyone, my name is Keegan Harris. I'm a PhD student at Carnegie Mellon University, and today I'll be talking about our work on strategic instrumental variable regression. So before I get started, I'd like to mention that this is joint work with my collaborators from the University of Minnesota, Daniel and Logan, as well as my advisors at Carnegie Mellon, Hoda and Stephen. So I'm sure as most of you know, machine learning models have been used increasingly to assess individuals' qualifications in high stakes opportunities, such as education. And this raises some possible concerns, but the one I'll really be focusing on today is sort of the downstream implications of these machine learning models. So in particular, there's this notion of Goodhart's law, which loosely states that once a metric becomes a goal in and of itself, it ceases to be a useful metric. And this area of strategic regression or strategic classification aims to formalize this. So strategic regression models this interaction as a game between a decision maker and a strategic agent. The decision maker moves first by deploying a decision rule to which the agent strategically modifies their features in order to achieve a better prediction under this decision rule. So under this setting, the goal of the strategic agent is relatively straightforward. They want to optimize the prediction that they receive, whereas the goal of the decision maker can depend based on the context. So one thing they might want to do is minimize their predictive risk. So minimize the difference between the agent's true label and the label that they predict. Another thing they might want to do is maximize outcomes for this agent population. So they might want to maximize the true label after feature manipulation in expectation over the agent population. And the third thing that I want to do is estimate causal relationships between observable features and outcomes. So as an example, consider a stylized college admissions setting under which a university deploys an admissions assessment in order to learn something or predict something about the student's college GPA. So knowledge of this admissions assessment will cause the agents to take some action. Namely, it'll cause them to study, whether that be for their schoolwork or for an SAT test or ACT test, something like that. This action that they take in turn will affect their observable attributes, such as their high school GPA and SAT score, things like that. And there's some true underlying relationship between these quantities and success in college as measured by their college GPA. So what makes this process not straightforward is this unobserved confounding variable of student background, which affects how easy or hard it is for them to study, maybe what scores they would have gotten had they not studied, and also it affects their college GPA directly as well. So we can formalize this model a little bit more. So in general, we say the principal deploys some assessment rule theta to make decisions about an agent's outcome y. Knowledge of this assessment rule causes the agents to take an action denoted by A, which affects their observable features denoted by X. Additionally, we assume there's some true causal relationship theta star between observable features X and outcomes Y. On top of that, we say that each agent from the population is described by their private type. This private type affects the actions that they take, their observable features, and their outcomes directly. So our key observation is that in this setting, the decision rule theta deployed by the principal is a valid instrument. So we can do something called instrumental variable regression. So what is instrumental variable regression? So basically it's this existing technique where the idea is to use a third variable, often referred to as an instrumental variable, to estimate the causal relationship between two observable variables, X and Y, under the presence of some confounding term that's unobservable, U. So in this setting, we use theta as our instrumental variable. There are several conditions for theta to be a valid instrumental variable. One being that it's independent of U, which is satisfied, and another being that it only affects Y through X, which is also satisfied. And this sort of makes intuitive sense because varying theta allows you to vary X and Y sort of independently of U, which allows you to estimate this true relationship between the two. So in particular, we do something called two-stage least squares regression. Basically what that is given a sequence of decision rule observable feature outcome tuples, we first regress decision rule theta on observable features X. We then regress theta on the outcomes Y, and then we can estimate this causal relationship using the two quantities we've estimated. So our main result is that given sufficient randomness in the decision rules and certain nicety conditions on the agent population we're making decisions about, we can recover an estimate of the true causal parameters, which approaches the true value of these parameters at a rate of 1 over root t, where t is our number of time steps. So, as I mentioned earlier, in the strategic regression setting, the decision maker can have several goals. And we already touched on causal parameter estimation. But what about the other two? What about if they want to minimize their predictive risk or maximize the agent outcomes? So a cool thing is that, to make a long story short, we can use this causal knowledge estimated in the previous round to accomplish these other goals. So for example, if the principal wants to maximize agent outcomes, they can solve a linear program parameterized by quantities we estimated during this two-stage least squares regression procedure. Similarly, if they want to minimize their predictive risk, they can run online gradient descent using these parameters they've estimated already as well. So we decided to evaluate our methods on a semi-synthetic college admissions data set. So basically what we did here was we took an existing college admissions data set and modified it for the strategic regression setting. As you can see on the left here, our methods denoted by blue are able to recover the true causal relationships in our data set, denoted by the dotted red line, whereas simple methods such as ordinary least squares that don't take this causal knowledge into account are not. And on the right, you'll see that, while this admissions data set doesn't satisfy all of the theoretical properties required for us to get this 1 over root t convergence, we still observe it in practice. So just to recap, we cast the strategic regression problem as an instrumental variable regression problem. And our main contribution is that we can view this decision rule deployed by the principal as a valid instrument. Additionally, under certain nicety conditions of the population and sufficient randomness in the sequence of decision rules deployed, we provide bounds for this causal parameter recovery. We can then use this knowledge of causal relationships to solve other principal objectives, such as agent outcome maximization or predictive risk minimization. And finally, we evaluate our methods on a semi-synthetic college admissions data set. Thanks for your time.